get inspired and get more focused on their research activities and so on. Also, we are very happy to see that people from Jadavpur, RP, Kolkata, Kharagpur are still upholding the legacy in RF domain. Our societies at GEC Barton Hill always associate with Indian Institute of Space Science Technology, Trivandrum, as we know that for progress, we need to associate with the best. And I especially am very fortunate to be a part of this association along with my undergraduate students. And special mention to Dr. Chinmoy Saha, Arjit Mitra, scientist VSSC ISRO, for mentoring our students for making some of them an asset in RF domain. As a true academician and a scientist, Kerala section is very fortunate, myself and our students, for your involvements in our society chapters that led to many high quality technical events apart from absent since you joined with ISRO IAST. On the last 17th, that means this 17th September, we are fortunate to have our MTTS get inaugurated by Dr. Ala Abunjalai, MTTS president. And yesterday also, we had APS Society Conclave led by Dr. Ehiya Andar, Dr. Siddiqui, etc. Now coming back, I would like to request the young students, especially the young students, to keenly attend the session, as there is a lot of challenges one has to face, starting from the scratch to the final implementation of these electronically small stuff antennas. In fact, I was familiar with this term only during my MTech days. Also requesting, instead of passing greetings or greetings, apart from other relevant information, you on the question and answer session raise your concerns so that the discussion will be more fruitful. And if our speaker is willing, for getting interrupted in between, it's up to Sanghamitra sir. Now let me introduce our speaker. Dr. Sanghamitra received his BSc degree in Physics Honor from University of Calcutta, followed by which he joined Radio Physics and Engineering Kolkata, where he pursued his BTech and MTech. After finishing MTech in 2013, he moved to Canada to pursue PhD from University of Alberta, where he is currently working as postdoctorate research assistant. His interest includes dielectric resonator antennas, tapered slot antennas, metamaterials, novel miniaturized dipole-like antennas, along with their time and frequency domain characteristics. He has been an active volunteer in various IEEE events, including international conferences, workshops, and other events since 2009, and served in Kolkata and Northern Canada chapter. He has published several journals to his credit. Now let me welcome, and we are privileged to welcome our guest and speaker of the day, Dr. Sanghamitra sir. And before that, I would like to give the virtual podium to Saha sir. Thank you, sir.
Do I really need to say anything anyway? Dr. Sanghamitro Das, who is like Shangho to me, like my younger brother. I know him from very early career when he was doing BSc Physics Honors at that time onwards. He has visited also IST and Trivandrum quite a few times. And I know him not only from early careers, he's associated with us on various capacity because of his mentor and his guide at Canada, Dr. Ashina. Is a very good friend of mine, and on certain problems we have worked together also. I see Latif present over here, so Latif knows we have worked on certain problems together, and we have done some joint publications. So he has very good understanding. He is a real engineer. He works in hand. He has spent a lot of time in anechoic chamber. There at Alberta, University of Alberta, they have the best facilities, one of the best facilities across the globe in terms of electrically small antenna characterization, the best type of anechoic chamber. So he have all the expertise, and he is young, he's very dynamic, and other aspect of him is very helpful. He has sometimes helps us also. Like they have very high quality systems and all. Sometimes on such simulations and etc. He has helped us. So I wish all the best to Dr. Dash for his career, and I am pretty sure that this particular session will be very beneficial for all of you who are trying to search some new problems towards your research direction. I don't want to prolong, so I hope this session will be very beneficial to all of you. So you may please proceed. Over to you, Anu and Sivada.
Thank you, sir. Now, it's my duty to introduce the speaker to you all. So, Dr. Sanghamitro Das received his BSc degree in Physics Honours from University of Calcutta, followed by which he joined the Department of Radio Physics and Electronics under University of Calcutta, where he pursued his BTech and MTech degrees. After finishing MTech 2013, he moved to Canada to pursue his PhD degree at the University of Alberta, where he currently works as a postdoctoral research assistant. His research interests include dielectric resonator antennas, tapered slot antennas, metamaterials, and novel miniaturized dipole-like antennas, along with the study of their time and frequency domain characteristics. He has been active on India in various IEEE activities, including international conferences, workshops, and other events since 2009. He served both Kolkata and Northern Canada's chapters. Sir, I welcome you to deliver the talk. It's a great privilege for us to have you here. Thank you, sir.
Thank you. So I'll start sharing with my screen, I guess. Can you see my screen?
Yes, sir.
Okay. So good afternoon, everyone. My name is Sanghamitro Das, and I'm currently a research assistant at the University of Alberta. First of all, I'd like to thank the IEEE MTD Society of Kerala chapter and the whole team of IEEE student branch of the Government Engineering College, Barton Hill, for coordinating and organizing this event. Next, I'd like to thank Shivada, and I don't know the other person who introduced me, for the nice introduction. And finally, I'd like to thank you all for making time to attend this webinar lecture. The topic of my presentation is electrically small antennas, where I'll talk about the different challenges and designing these antennas and some solutions as to how to cope with them. Tried to keep the presentation simple. However, like if you have any questions, I can answer them at the end. So please bear with me. Okay. So here is like a brief outline of my presentation. I'll start with a very brief introduction about myself. Then I'll describe what are electrically small antennas, their history, and how to design them, followed by some of their applications and the usual challenges that are faced while miniaturizing antennas and the available solutions. Next, I'll talk about the electrically small dipole-like antennas, mostly conventional and folded dipoles, and why I picked them for this particular discussion, followed by the different available miniaturization techniques. Then I'll describe some new methods for miniaturizing them, where I'll show some new solutions to the matching problem of electrically small dipole-like antennas. This is actually my own work, and I'll show some prototypes that I have designed. Following that, there will be a brief description about the quality factor of an antenna and how one can use the knowledge of the quality factor to resolve the issues of poor bandwidth that is caused by miniaturizing antennas. Finally, I'll conclude with a summary. So this is an aerial view of the North Campus of University of Alberta. And so this is basically the campus, the whole place. And this is like the city, downtown. And then there's a river flowing in between them. And here is my department, EC department, like right here. And this is like a photograph of my research group taken a couple of years ago. You can see me on the right. I found this photo particularly appropriate since Edmonton is a city that stays under snow for at least 7 to 8 months every year. Moving on to the actual topic. So what are the definitions of electrically small antennas? There are several given by researchers who we consider as kind of legends in the field. I have shown three definitions here. First one was given by Harold Wheeler, who said that an antenna that occupies a volume less than the radiant sphere can be called an electrically small antenna. And the radiant sphere is essentially a sphere with a radius of 1 radian, that is lambda by 2 pi. Next definition was given by Sergei Shelkin, who said an electrically small antenna should have a largest dimension that does not exceed 1/8 of an wavelength. The definition we use for today's electrically small antennas was actually given by Ronald King, who is actually a father figure of WAV-type antennas, who said that an antenna would be electrically small if the factor Ka, which is the electrical size of the antenna, less than 0.5. Here, K is the wave number, or 2 pi by lambda, and A is the radius of the smallest sphere that just circumscribes the antenna. This sphere is also sometimes known as the Chu sphere, since it becomes important to estimate the quality factor of the antenna. I'll come to that later in my presentation. Now, one might think that the topic of electrically small antenna is a recent trend of research. Sure, there have been like a lot of progress in small antennas research lately, but electrically small antennas existed from the very early days of antennas, when the idea of wireless communication just started to take shape. The first instance that I could find was a patent by the legendary Thomas Alva Edison in 1885, who proposed two top-loaded monopole structures for communicating between 2 points on land or between land and sea. So basically, these are top-loaded monopoles that are simple monopoles loaded with shunt capacitances, as you can see here. This is one way of making monopoles electrically small. So the next example was from Heinrich Hertz, who we owe for giving us the current versions of Maxwell's equation that comprise only 4 equations compared to Maxwell's originally 20 equations. He did an experiment in his lab at Karlsruhe University between 1886 and 1889, which is famously known as the spark gap experiment. There also he used like a top-loaded dipole. As you can see here, this is the feed and this is the top loading, like end loading. Top-loaded dipole as his transmitter, and he used like a loop for his receiver, and he received sparks at this gap. So that's how it's the spark gap experiment. Followed by them was Marconi in 1901, who was successful in sending a signal across the Atlantic from England to Canada. To this day, almost all broadcast antennas are electrically small. The reason being, broadcasting used to be done at medium to very high frequency ranges, which is basically high kilohertz to low megahertz range, where the antenna dimension is of the order of several tens of meters to close to even 100 meters, which is pretty huge. So it makes sense that these people used electrically small antennas. Next, I'll talk about how to make an antenna electrically small. Now, it is well known that for efficient operation, antenna dimension should be of the order of half of a wavelength or a full wavelength sometimes. Now, to convert the antenna into an electrically small antenna, we need to bring down its operating frequency. So smaller operating frequency means larger wavelengths, and for the same physical size of the antenna, smaller fraction of wavelength. How we can do it? The trick is to slowing down the phase velocity in the antenna. That is by applying a slow wave structure. Once the phase velocity is slower, it will take longer amount of time for the phase to traverse through the antenna, thus slow wave, resulting in larger phase differences compared to what it should have been at the original operating frequency. Just to give you an idea, let's say we have a dipole operating at 1 gigahertz, that is half wavelength at 1 gigahertz. Now, lambda by 2 means 180 degrees. Now, let's say by introducing one of these slow wave structures, one can bring down the operating frequency to 500 megahertz. In normal circumstances, 500 megahertz would only offer 90 degrees of phase, but due to the presence of the slow wave structure, now it is offering 180 degrees. That's how we can make the dipole work at its miniaturized half wavelength frequency, that is like 500 megahertz. The simplest example of slow wave structures is to extend the current path on the antenna by making structural modifications like forming like a helix or like a meander line dipole antenna. Other examples include fractal antennas like this Van Gogh fractal and the Sierpinski fractal monopole. Other than that, one can apply artificial materials like metamaterials or artificial magnetic conductors. One other technique is there that uses high permittivity dielectrics. However, it's not recommended for antennas because high permittivity dielectrics tend to hold the electromagnetic wave rather than releasing them or radiating them. Thus, it can severely degrade the antenna's radiation efficiency. So, this slide is about where electrically small antennas are applied. I've already mentioned about the broadcasting antennas. Other than that, they are used in different mobile communications like near field communications, wireless LAN, Wi-Fi, WiMAX, and different multiple input and multiple output systems like the ones that are known as MIMO. Also, these are used extensively in sensing and identification, like biomedical and environmental sensors, machine-to-machine communications, one example of which is Internet of Things, and then body-centric applications, on-chip antennas, RFID. I've shown some pictures here of the antennas of the devices that use electrically small antennas. So the challenges of miniaturization. The major challenges of miniaturizing an antenna are reduced bandwidth and poor efficiency. And also, since the process of miniaturization lowers the input resistance and makes the antenna highly reactive, the matching becomes difficult with respect to, let's say, a typical source impedance of 50 ohms. Now, bandwidth and efficiency of a miniaturized antenna are usually constrained by physics, so it cannot be improved without significantly modifying the structure. However, the issue of matching can be resolved by employing external matching networks, some typical example of which are L or T or pi sections or single or double stub matching, then single and multi-stage transformers. But again, these matching networks can become bulky at low frequencies because everything is based on the like wavelength of that particular frequency. That's how it can defeat the purpose of miniaturization. So basically, you want to make the antenna small, but the remaining matching structure can be big enough to make the whole system size big. So an example of a small dipole antenna is shown here. When miniaturized, a dipole antenna becomes capacitive, so and its radiation resistance decreases. Now, to compensate for the capacitive reactance, one will need to have an inductor first. That's the first stage to the left. And then some sort of impedance transformer to transfer the small radiation resistance to the source impedance, like 50 ohms or something. And thus, although the antenna was made small, the remaining circuits can make the whole system large. Moreover, matching structures can introduce additional losses, which may further degrade the radiation performance, like the radiation efficiency of the antenna. However, if one can somehow introduce a matching mechanism inside the antenna, like embed it inside the antenna structure, the issue of additional size and the loss can be overcome. So for this antenna, for this talk, I'll be focusing particularly on dipole-like antennas, as they're the simplest of all antennas that we come across. They're compact, less expensive, and has very well-defined radiation properties. As a result, they're probably the earliest antennas put to use, as I have shown you a few slides earlier. Also, dipole antennas and their derivatives like monopoles, loops, And folded dipoles are used extensively in mobile and sensing applications. Since for these applications, antennas must be very low profile and lightweight. Also, small bandwidths and low radiation efficiencies are often tolerable for these applications. Small bandwidths just to give away the signature of a sensor, and small radiation efficiency to send the signal over a relatively short distance. Now, for the miniaturization techniques of regular dipole antennas, perhaps the most common techniques is to load it with a series inductor or a shunt capacitor. That is also known as top loading, as I mentioned before. The series inductive loading, this one, as you can see, both in lumped and distributed form, helps realizing a longer arm length in a more compact fashion. This is an example of a meander-like dipole. Sorry, monopole, which is like a crude example of embedded matching. What happens here is that longer the arm length is, it results in the required inductance for the miniaturized antenna to cancel its capacitance. And then it increases the input resistance also because of the arm length. But this resistance comes in the form of ohmic resistance and not radiation resistance. As a result, although the antenna is probably self-resonant at the miniaturized frequency, the radiation efficiency becomes very poor. The next example is shunt capacitance or top loading. So as you can see, like there are two discs at the ends, and that provides the shunt capacitance across the dipole. So it relaxes the zero current condition at the ends for dipole antennas, which essentially simulates a longer dipole antenna. The radiation efficiency for this kind of miniaturized antennas are much better, owing to the uniform current distribution. So if the current doesn't go to zero here, it will be more uniform, and that's how it will radiate more. But although the antenna height becomes small, the lateral size of these antennas that actually decide the level of miniaturization can be large. So for other miniaturization techniques include metamaterial loading, where half wavelength is basically realized over a much shorter length using the exotic dispersion properties of the metamaterial, either by surrounding the dipole with an ENG shell, which is epsilon negative materials. So that can be simulated by surrounding the monopole with a simple inductor. Or otherwise by loading the dipole periodically using transmission line metamaterials. Finally, there are inverted F structures where the compactness is achieved by simply bending the monopole. And that's how like a low profile can be achieved. But they're still quarter wavelength long, but compact in the sense that they don't occupy as much vertical space like a common monopole. These are particularly useful in the presence of ground planes, and a lot of mobile antennas are actually inverted. However, further compactness can always be achieved by either by meandering or folding. So basically any of the previous techniques you can apply to this IF antenna, and you can miniaturize it even further. Okay, now let's have a look at folded dipole antennas. So these antennas, as you can see here, are constructed basically by joining two conventional dipole antennas at their ends with an infinitesimal separation between them. It is also resonant at half wavelength, just like a regular dipole, and radiates an omnidirectional electric dipole-like pattern. And the miniaturization techniques for folded dipole antennas are very similar, again, because it works on the same principle. The simplest techniques are loading the antenna with a series inductor, just meander lines, or like a shunt capacitor. As you can see, this is the driven arm, and this is the folded arm, and this is the top hat, basically. Other than that, metamaterial or conventional phase shifters can be used to realize an electrically small folded dipole antenna. Here, the phase shifters provide sufficient phase difference between the two arms of the folded dipole antenna to make them radiate in phase, so that it can still have a high radiation efficiency. And also, like, it helps in matching. So now let's have a look into the input impedances of a conventional dipole antenna and a folded dipole antenna. First of all, unlike the conventional dipole antenna, the input impedance of a folded dipole antenna is adjustable. Thus, it can be advantageous. I'll show you later. Although at the expense of increased antenna footprint, that is either by adding more number of arms or by realizing different ratios of cross-sectional widths of individual folded dipole arms. Now, I'd like to draw your attention towards the input impedance plots of the conventional and folded dipole antenna. Now, as you can see, the folded dipole antenna has an additional anti-resonance before the typically used half-wavelength resonance band, that is FR. It is similar to that of a loop antenna, and you can imagine folded dipole antenna as a modified rectangular loop where the shorter sides have been shortened even farther in order to make it look like an electric dipole compared to the loop, which is a magnetic dipole. Typically, the first anti-resonance, this one, is never used because the first reason is very high real part of the impedance. So you cannot really match to 8,000 ohms. And the second reason is the current distribution. So at this first anti-resonance, the current distribution of folded dipole looks like this. So basically, it's a half wavelength circumferential current distribution. And as you can see, the currents on the two arms are oppositely directed. So they kind of cancel somewhat in terms of radiation. And so basically, this folded arm has higher amount of current. So it still radiates because of that, because of the imbalance. But it's not like when the currents are in phase in both the arms. So that's how it loses some of the radiation efficiency. Now, can this be an advantage over conventional dipoles for designing electrically small dipole-like antennas? The answer is yes, we can make use of that anti-resonance. And I'll show you how in the next few slides. And interestingly, this can be achieved by simple reactive loading techniques, just inductive and capacitive loadings. And we'll be using a series inductive, like I've showed you before, but a series capacitive loading instead of the shunt capacitive or top loading cases that I've shown. So basically, this series capaciting loading will be crucial for this particular case. This is like basically what I did during my PhD. So before going into that, let's have a look into the impedance trends, like what happens when we load a folded dipole with series inductors on both arms. So as you can see, for series inductive loading, the reactances are placed like halfway between the feed and the end on both arms. And with increasing inductive loading, the anti-resonances actually shift towards lower frequencies, which is like basically miniaturization. But the real part, which we'll have to match to, actually keeps on increasing. So we cannot yet match to these resonances yet. For series capacitive loading, the opposite happens expectedly. So basically, the resonance move towards higher frequencies now because capacitance is basically negative inductance, right? And the real part of the anti-resonance decrease, but it's still not low enough to be matched directly. So as you can see here, it's about 2000 ohms. Now note one interesting thing here, that is a new resonance appears before the anti-resonance as a result of the series capacitive loading. This is basically a series resonance of the already inductive antenna. So unlike dipole antennas, folded dipole antennas are inductive or miniaturized. And the series capacitive loading that we have applied. So it's basically that series LC resonance that you are seeing here. But again, like the real part at these resonances are very small, like very close to 0 ohms. So we cannot match at these points either. But then what is the purpose? So that's what I'll show you in the next slide. So like I mentioned, both these new resonance and the anti-resonance are not suitable for matching in their current form. But what if we can place them close to each other, such that the low input resistance at this resonance can take advantage from the high input resistance at this resonance? And the new resonance, if you can place it somewhere beneath this rising slope of the anti-resonance, so you can pretty much match to any source impedance between 0 and let's say 4000 here. So 50 ohm is just as easy. So just give a number, 50 ohms, 75 ohms, 100 ohms, and you can match there. So what we found was it is possible to do that if we are using like both inductive and capacitive loadings in series, and we use a very large loading inductance and a very small loading capacitance, which is shown by the 3D plot here. So that's where the two resonances actually approach the closest. But then we found, like I've showed you the examples of symmetric loading so far. Then we found that for symmetric loading, the values of L and C becomes unrealizable. So basically L becomes like very, very large and C becomes very, very small. So as a remedy, we decided to try introducing asymmetries in the loading scheme. So basically make one are more inductive and other are more capacitive. So for like I've showed here, this for this case, the folded arm was made more inductive and the driven arm was more capacitive. And for this case, the opposite. So, and it's probably not very clear from the plot, but for this particular case, the difference between these two resonances actually decrease. But the opposite happens for this case when the folded arm is more capacitive. So we'll be making use of both of these. So this will use for matching with real source impedance like 50 ohms, and this will use for matching with complex source impedance. I'll show you one example later. Okay, so let me show you the first prototype that we have designed for inherent matching with a real source impedance. So we selected a folded dipole, obviously, of length 38 millimeters, which is half wavelength around 4 gigahertz. And the selected dielectric substrate is Magnetron 4 with these specifications. The reference impedance for this particular case, we chose 200 ohms. And I'll tell you like after a few slides why we chose this particular value, not 50 ohms. And then as you can see, there is a CPS transition that actually feeds the antenna. And our target was to achieve good matching at a miniaturized frequency point, 75 by 75% at 1 gigahertz. So the corresponding Ka value, that's the electrical size that I have mentioned before, is 0.4 at 1 gigahertz, which is less than 0.5. Thus, it is an electrically small antenna. And for this particular antenna, we used a fully asymmetric loading scheme. So if you remember from the last slide, when the folded arm is inductive and the driven arm is capacitive, the difference between the two resonances decrease. So that's what we tried to do by making them fully asymmetric. And for additional degree of freedom, which is strictly not required, we tried to implement like two different arm modes here. These are some other parameters like for the design. So as you can see, the L value is 43 nanohenries. That's the inductive loading value, but that's quite high. And the required capacitance value was in femtofarads, which is pretty small. And we realized that by just distributed capacitance. Now, as you can see, now these two resonances are like right next to each other. And we got like a good matching at 1 gigahertz with respect to 200 ohms. And the 10 dB bandwidth was only 7 megahertz, which is 0.7%. And it's expected because I told you earlier that when you're miniaturizing an antenna, you're losing bandwidth, basically. The radiation efficiency and the gain of the miniaturized folded dipole antenna were found to be 72.3% compared to 5.8% of equivalently unloaded folded dipole antenna. And the gain was minus 0.9 dB compared to minus 12.2 dB for the unloaded antenna. And we got like omnidirectional pattern, obviously. The reason for this difference, you can tell from these current plots. So if you see the unloaded antenna, the currents are almost equal and opposite on the two ends. But for the reactively loaded antenna, the first prototype that I've showed you before, you see like small currents here and large currents on the folded arm. So there is a like a difference between the current densities, which actually results in the overall radiation. So we developed a spatial feed structure, which is this one for the antenna, because we need to feed dipole-like antennas, not dipole-like antennas, like dipole antennas with a BLN, which is basically unbalanced to balanced transformer. Unbalanced transmission line like coaxes, SMAs, those things can cause like, you know, a fall in radiation efficiency for the balanced antennas like dipoles. So we need that BLN transformer. So this feed structure is essentially a BLN and not a matching network. So this converts a coaxial MMCX connector into like the balanced CPS, these feed lines. So the total length of the transition is like this length is only 0.08 lambda at the operating frequency, which is much smaller than conventional microstrip to CPS transitions, which are about like quarter wavelength or even larger sometimes. So for this, there are two major components. One is the 50 ohm M6 connector, and the second is like a mini circuits transformer. So this transformer actually works as a BLN. So this is a center tap transformer with a trans ratio of 1:4 that essentially transform this 50 ohm coaxial input to 200 ohm. So that's how we chose 200 ohm in the first place to match the antenna. And we also checked the response of this feed network only, and we found like it has a very broadband and low loss response. So that can only ensure that it will have a minimal impact on the antenna performance. So for practical realization, this particular inductor was used, which has inductance of 35.45 nanohenries, which is less compared to the required 43.2 nanohenries that I've showed you before. And this was done deliberately so that we can design without getting restricted by the availability of a particular inductor. Also, the inductor was assigned with a finite quality factor, which is basically accounting for the practical losses in the inductor. And now to compensate for the lower inductance, we just slightly modified the folded arm. We added these sections, and the length of these sections will provide the lost inductance. Yeah, okay. So for the final results, we just fine-tuned the antenna, and we got again good matching for this particular value of this vertical section length. The loading capacitance was slightly adjusted just to bring it to 1 gigahertz. And the 10 dB bandwidth was 15 megahertz, which is less than, which is actually more than the 7 megahertz that we have seen before. And the radiation efficiency is now 35.3% compared to 72% that we saw before because of the practical losses in the inductor. So that caused the drop in radiation efficiency, but at the same time, it increased the antenna bandwidth. Although I haven't shown here, we have compared these results with an inductively loaded conventional dipole antenna. And we found like the radiation efficiencies are comparable. However, for an inductively loaded conventional dipole antenna, the flexibility to fine-tune the input resistance in order to achieve good matching is much less compared to this folded dipole antenna that I'm showing here. So during measurements, the actual inductance value was found to be slightly smaller because of the finite tolerances of the shelf inductances. That always happens. And so we just slightly adjusted this vertical length value. And the measured return loss was at 999 megahertz, which is just 1 megahertz apart. And the bandwidth was 14 megahertz, which is pretty close. And also for patterns, we got good agreements. So this large discrepancies in cross pole was because we couldn't find an accurate 3D electromagnetic model of the transformer. So we had to kind of leave it out as a parasitic. So we couldn't account for the actual currents there, and that might have caused this difference in cross pole. And the discrepancies here is because of this vertical mounting stand, which was causing some blockage during measurements. So, and the next prototype, what we tried to do is we tried to remove this uncertainty due to the of the shelf inductance, and we tried to make it fully printed so that you can just print the whole thing and without needing to solder anything. For this, you can see the whole folded arm was meandered, and we use these gaps as capacitance. And it was designed for 902 to 928 megahertz, which is the allocated UHF ISM band in North America. And the target miniaturization level was once again 75%. Thus, the antenna length is 41 millimeter at 915 megahertz, which is basically the center frequency of this selected band. And but like while simulating, we came across one issue here, which is like the memory requirement for this. Because it has a lot of fine features, it required a lot of memory, almost 110 gigabytes for one single frequency. So we had to relax the convergence criteria slightly, but still it took a very long time. So what we can expect from the major return loss peak is it might slightly differ from the actual simulation, which I've showed here. So during this S11 measurement, like as you can see, the peak return loss got shifted to 955 megahertz, which is about 4% shift. So what we did is we just simply adjusted the loading capacitances to bring back the peak to 915 megahertz. And the measured 10 dB bandwidth was 25 megahertz, which is pretty close to 23 megahertz that was simulated. So one thing is clear. So for these folded dipole antennas, only thing that you have to do is you have to update the inductive and capacitive loading. You just have to modify those two, and you can pretty much match to any frequency with respect to any source impedance. So that's the flexibility of this design. And this is the pattern for the fully printed antenna. It has similar features like large cross poles and like this discrepancy due to blockage. So next one is a very interesting one. Before I go towards that, so what are the applications for like these kind of antennas that are matched to real impedances? So it can be designed as a part of system transceivers, and so basically, as you can see here, this is like an architecture block diagram. And these usually have its own onboard power supplies. And some examples are like environmental sensors, bioimplants like pacemakers. As you can see here is a tiny pacemaker next to a vitamin pill. and capsule endoscopy to take pictures inside, and then machine-to-machine communications, etc. Yeah, so next one is more interesting. So like I said earlier, this technique can be used for designing electrically small folded dipole antennas for matching with complex source impedances. A typical example of matching with complex source impedances is RFID. It works as a backscatterer that is connected to an IC. So basically this tag scatters back the signal, and that's how the reader knows like the RFID tag is here. And the IC usually have like a complex impedance. So you have to match to that particular complex impedance conjugately. They're used for like asset identifications, tracking, dielectric sensing, healthcare, safety, security, all these. There's a lot of applications for RFIDs. So, like I said, an RFID system has two parts, one reader and one tag. So the reader consists of the reading antenna, which is typically not electrically small, and the reader module, which actually generates the coded messages that is used to actually track this tag. So IC has like an ID stored in memory, and based on that, this reader will like generate a coded message. And then there's a computer for just display, like where you are reading the same ID from the tag. So that's how you know this is one tag. It's not the same as the other tags. For tags, it can be of three types based on whether or not it has an onboard power supply. So active obviously has an onboard power supply here, which is so basically, okay, I'll tell you the difference after I finish this sentence. So other than that, semi-passive and then passive. Passive doesn't have any power supply. So what happens for passive is once the antenna picks up any signal, it activates the IC, and then IC sends a signal back to the antenna, which is sent back to the reader. For active tags, there is already a battery on board. So basically, this can transmit without even accepting any signal. So for active tags, the distance of tracking can be more compared to the passive tags. But here we are mostly interested in passive tags that are matched to complex input impedances. And obviously, since there are no battery on board, these are like the simplest and cheapest. And like I said, typically consist of an ESA and an IC chip. Okay, so the IC chip in RFID is usually capacitive. So that's how the antennas must have an inductive input impedance. Now, if you remember, like for this example, the antenna was only inductive between the two resonances, the new resonances and the anti-resonance. Before that, it's capacitive because of that series capacitive loading that you have placed. Basically, the wider this region is, the larger is the range of workable frequencies in this range. So that's how we'll need to increase the separation between these two resonances, unlike what I have shown you before for matching with real impedances. So, and typical RFID parameters are antenna to IC power transfer coefficient, which is basically the matching defined by this parameter tau. If it is 0, it's completely mismatched. And if it is 1, it is fully matched. And the read range, obviously. So basically, that's the tracking range between the reader and the tag antenna. And for this design, we decided to use lumped inductors to increase accuracy and also reduce simulation time based on our past experiences. And this was also designed for the same UHF ISM band in North America. And once again, the target miniaturization level was 75%. So this is like a schematic. And these are the values of different dimensions and the inductance values. So we use this particular inductance and this particular IC chip. And as you can see, this is the capacitive complex impedance of the IC. So after fine tuning, we got like a good matching. So basically these dotted lines are the imaginary parts. So the blue dot lines are the conjugate of the IC impedance. and the red dot lines are actually the uh, inductance from the antenna. So as you can see, at 915 megahertz, we got like this reactive parts cancelled, and the resistive parts are pretty close to each other. So that's how we got like a good matching, which is we got like tau equal to 0.98, very close to 1. And the radiation efficiency was 30.9% because we used a real model of the inductors with loss in terms of the quality factor of the inductor. So then we measured the read range. So for that, we use this reader antenna, which is basically a right-hand circularly polarized antenna, and this reader module. So as you can see here, this is simulated versus measured reading range. We got 8 meters at 915 megahertz for the simulated, and we got almost 7.8 meters at 908 megahertz, which is 7 megahertz shifted for the measured case, which is probably because of the finite tolerances of the lumped inductors that we have used. And we also measured the read range pattern just to ensure that it has like an omnidirectional coverage around the tag antenna, so you can track it from almost all directions except for these places, just like a dipole. So so far I've talked about how one can deal with the matching problem for an electrically small dipole antenna, including my own works, like these three, which you can use for matching with both real and complex impedances. So there's one other problem remaining for designing electrically small antennas, that is the bandwidth problem. So for that, first I need to describe what is the quality factor of an antenna. So the Q factor of an antenna is a very valuable metric that connects the electrical size of the antenna to its bandwidth and radiation efficiency. And it is particularly useful for describing the performances of the electrical small antenna. So this Q factor is analogous to the Q factor concept of resonators, filters, and inductors. Except for the resonators, we require a very high Q factor. On the other hand, for antennas, the Q factor must be as small as possible in order to maximize the loss in the form of radiation. So from antennas, we need the loss. The most important characteristics of Q factor is that it is inversely related to the fractional bandwidth of the device. Higher the Q factor is, sharper is the resonance and smaller is the bandwidth. So this is the most fundamental definition of Q, that is the inverse of bandwidth. And it is also defined as the ratio between the stored energy to the dissipated power, which for antenna actually comprise the radiation and the loss powers in terms of ohmic losses and dielectric losses. Now, for a given electrical size of an antenna, there exists a lower bound of this Q, which in turn determines the maximum fractional bandwidth that can be achieved. I'll take your questions at the end. Is that okay?
Sir, it's okay.
Okay. So I'm pretty close to the end. So. Okay. So the lower bound of Q was studied by several researchers, starting from Harold Wheeler and L.J. Chu in the 1940s to MacLean in 1996. So Chu calculated the minimum limit of Q by assuming a vertically polarized dipole antenna that was fully enclosed by the smallest possible sphere, that is the Chu sphere, as we know it. And then by expressing the radiated fields outside the sphere as a sum of several spherical modes by using spherical Bessel function expansion. However, there were some errors in his expression, which was later corrected by Collin and Rothschild first, and then the correction was confirmed by MacLean. The current form of Chu limit, which is also known as Chu-Harrington limit, for a generally lossy antenna is given by this expression, where the radiation efficiency accounts for the loss in the antenna. However, there are several assumptions that one must remember before using this expression. That is, the antenna must radiate a single TE or TM mode. Then the stored energy should not be considered within the Chu sphere. It has to be considered outside. Now, this causes a problem because an antenna that does not fully occupy the volume inside the Chu sphere, like the dipole that I've showed here, will have some stored energy in its vicinity in real life, which goes unaccounted for. And that's how the calculated Q lower bound is actually smaller than what it should have been for the particular dipole antenna. Remember, the stored energy in the expression of Q was in the numerator. So if you are losing, if you're not accounting for these stored energies, your this Q factor that you're calculating is actually lower than what it should have been. There exists some other lower limits, which was devised by Thal and Gustafsson, which is obviously like greater than the Chu-Harrington limit. And these are particular case based. So basically, for a dipole antenna, one should have like one particular lower limit, but for a patch antenna, the lower limit will be different. So what is the trick for maximizing bandwidth for these cases for electrically small antenna? So the antenna must occupy all the space inside the Chu sphere. That way, there won't be any unaccounted stored energy inside the sphere, and the Q lower bound for this particular antenna will be very close to the actual absolute like lower limit, that is the Chu limit. That's how for a volumetric antenna, say for a spherically shaped antenna, will have a larger bandwidth than a planar antenna, like a patch, which will again have like a larger bandwidth than a wear antenna, like dipoles. Now, there are some researchers who have claimed to have beaten the Chu limit and thereby achieved bandwidths larger than the maximum limit. But once again, like these claims remain somewhat controversial to this date. There are always something that they might have not accounted for or something. I won't go much into it, but I'll show you one example after a few slides where the Chu limit does not hold. So how we can actually estimate the Q factor of electrically small antennas? Note, not the lower bound, but the actual Q factor of the antenna. For that, we'll have to estimate the stored energy and the dissipated power, for which we'll have to have the full knowledge of antenna fields in the full 3D space. Now, this could be computationally difficult because you need to know all the fields at all these like 4 pi steradian points. In their what I should call a seminal paper, Stephen Best and Arthur Yagjian attempted to derive simpler expressions for estimating the quality factor. This is the only paper to my knowledge that gives us expressions for easily estimating the Q factor using just the input impedance or the VSWR bandwidth and some minimal field integrations on the antenna. They have managed to relate the fields of the antenna to the input impedance of the same antenna, and thus simplified the expression for the Q of the antenna. They have given 3 expressions in their paper. The first one is from the fields. As you can see, these R and X's, basically they are the real and imaginary parts of the input impedance, and the prime is basically frequency derivative. So basically it's dx d omega, and these parameters WL and WR are loss and radiation energies, which are calculated from the current distribution on the antenna, integrating over the dimension of the antenna, and this can be found from the far field. A much simpler expression is this one, which is basically calculated entirely from the input impedance, and this one, which is calculated from the bandwidth. And as you can see, this beta factor is related to the selected VSWR level. Now, there are assumptions here as well, mainly for the last two expressions. So basically, the assumptions are the antenna needs to be resonant at the operating point and it should be well matched. And the second and most important assumption is there shouldn't be any other resonance present within the selected VSWR bandwidth. So if there are more than one resonance present in, let's say, 10 dB bandwidth, you should go towards 20 dB bandwidth where there might not be like any other resonance present. So for conclusions, these definitions, all these three definitions, work at both resonances and antiresonance. So you can use these expressions for a very for estimating the quality factor of the antenna over a very wide range of frequencies. It's not resonance specific. And for a singly resonant antenna, as you can imagine, these three quality factors are approximately the same. Okay, so time for some example where bandwidth has been maximized for dipole-like antennas. Again, Stephen Best was the only one who did like a commendable job by designing a wide array of antennas and estimating their quality factors. These data are taken from his papers only, and here also a folded dipole proved to be advantageous compared to a conventional dipole antenna. See the first example. So this is a conventional dipole antenna where the antenna arm is twisted in the shape of a spherical helix in order to occupy the full volume of the Q sphere. However, the downside was it resulted in a small input resistance. So it was close to like 2-3 ohms. Thus it couldn't be matched. However, if we use a folded dipole for this case, and all of whose arms are like shaped like spherical helix, and you just basically feed it at one of these points, either here or here. Several of these issues can be addressed. So the first one is the input resistance. Like once I mentioned before that you can increase the input resistance of a folded dipole or decrease it by changing the number of arms. And that's how you can bring it closer to 50 ohms and you can just match it easily. So the resistance actually increases by a factor of n square, where n is the number of folded dipole arms. So for 4 arms, the impedance can be increased 16 times than the equivalent conventional dipole antenna, which had an impedance of 3 ohm, and 16 times of 3 ohms is 48 ohms, which is pretty close to 50 ohms, and you can easily match these antenna, although it is of the same electrically small size. Now, once again, more number of folded arms actually means all the currents in these arms are radiating in phase if you are operating at the miniaturized half wavelength frequency, unlike the resonances that I have used in my own work. So you can achieve a high radiation efficiency, and Stephen Best got around 97%. And also, more number of folded arm means better utilization of the spherical volume within the Chu sphere. So it's like densely packed. So it will result in a lower Q, and that's how like more bandwidth. So Best found the lower bound of the antenna, lower bound of Q factor for the antenna was close to Thal limit, which is essentially 1.5 times the lower bound calculated by the Chu-Harrington expression. It should be noted that for dipole-like antennas, the minimum possible Q cannot go below the Thal limit. So he actually was able to attain that limit by using multiple arms folded dipole antenna. Now let's talk a little bit about bandwidths, because this is a tangible quantity that is used in real life, not the quality factor. So is bandwidth absolute for a particular case, or is it relative? This brings us to the first case, that while estimating the quality factor for a real-life antenna consisting of a feeding structure, for example, like a matching structure or whatever, the Chu sphere must include the matching network as well. Now, a matching network can be designed using Bode-Fano technique, which is a very popular technique to design matching networks to yield an overall input impedance response, which will result in a wide bandwidth. But since probably the size of the Chu sphere is not changing, the maximum possible bandwidth defined by the Chu-Harrington expression is limited. But by using Bode-Fano technique, one can realize a bandwidth greater than the maximum limit. Can we still use the expressions for the Q calculations? That becomes the question. And next one is for an antenna whose input impedance is not exactly equal to the reference impedance, say 50 ohms, which is the center of the Smith chart, but is close and have small reactive parts around the target frequency. So as you know, like in order to match with the 50 ohms, you don't strictly need 50 ohms. An impedance like 42 plus J 2 ohms will also work. That will also give you a very good return loss. So that was the trick that that was used here. So it's also like one of Stephen Best's papers. So this particular case that doesn't go through the center of the Smith chart or it's not matched perfectly will always offer a larger bandwidth than this one. So again the same question: can we still use the expressions for Q calculations? And so this might remind you of multi-resonant antennas that use multiple resonances for bandwidth enhancement. And you're right, Bode-Fano technique is basically that. So once again, like for wider bandwidth, can we use any of these Q expressions? And also the question is, can they violate the lower bound of Q defined by Chu-Harrington limit? So Stephen Best answered in his 2006 APS paper that we can use QZ, which is the Q factor estimated from the input impedance, and it does not violate the lower bound. But when you are comparing QZ with Q bandwidth, you need to have like a very small VSWR level, like he showed in this plot. When the S is basically the VSWR level, when S is small, they almost overlap. But then in the next year, he teamed up with Howard Stewart and Arthur Yagjian to compare the Q factors for this antenna. So for this antenna, only one of these arms is fed and all the other arms are parasitic. And the matching can be determined by changing the number of arms and these semicircular sections. So this also occupies the full volume of the Chu sphere. Now let's have a look into the input impedance and the S1. So as in the input impedance, as you can see, there are multiple closely spaced resonances and anti-resonances. This result in a wide bandwidth, like you can see the 10 dB level here, wide multi-resonant bandwidth for the antenna. Now, when you are comparing the different Qs, so this dashed line is actually the lower bound calculated from the Chu-Harrington limit. So as you can see, although Q exact, which is the QF that I have defined before, does not violate, which is calculated from the fields, the Q factor that was calculated from input impedance actually does violate the lower limit. And QBW, the one calculated from bandwidth, doesn't really match because they considered a very high VSWR level, about at 3 dB. But they should have actually done it like here at 30 dB or something in order to match these two. So now there are several questions based on the observations they had. So this QZ quality factor violates the lower bound. Sorry, this would be Q lower bound. But this quality factor is actually inversely proportional to the fractional bandwidth, which is the first definition of Q. But Q exact, which is estimated from the fields, which although it seemed more accurate because it was estimated from the fields, is not inversely related to the fractional bandwidth. So Now, this is the question. So which one is important? A quality factor that is inversely related to the bandwidth, or a quality factor that cannot be related inversely to the bandwidth, but abides by the Chu limit. So this doesn't violate. Now, I'd like to remind you one more thing. That is, the lower bound expressions for Q was estimated for an antenna radiating a single TE or TM mode in its operating bandwidth. So can we really use this as the lower bound for a case of a multi-resonant antenna? So this still remains as an open-ended problem. And so basically we are also working on like our own version of a wideband electrically small antennas, but since it's not published yet, unfortunately, I'll not be able to show you the data for that. So just to summarize, the two main issue of electrically small antennas, that is matching and bandwidth, can be resolved. For matching, a folded dipole antenna will be an ideal candidate since its input impedance can be easily engineered by simple reactive loading or by varying the number of arms and individual arm widths. And matching can be achieved for both real and complex source impedances, which is a big advantage. And the same technique can be applied for loop antennas also due to the similarity between their input impedance patterns. And the issue of bandwidth, on the other hand, can be resolved by realizing a spherical shape for the antenna. However, for most of the cases, it will still be bound by a maximum limit for most of the cases. And finally, there still remains questions about the applicability of the quality factors and the lower bounds, particularly for multiple resonance antennas. So these are some of the references that I have used, and that is it. Thank you very much.
Thank you, sir. So we have a couple of questions in the chat box.
Okay, hang on. Let me just.
Okay, sir.
Can I maybe stop sharing?
Yes, sir. Of course.
Okay. Okay. Oh, there's a lot of conversation. How the impedance has been calculated over the function of length. So basically, the x-axis, which I denoted as L by lambda, is frequency, right? So you have a fixed physical length, and based on the wavelength, that L by lambda factor actually changes. So that's basically frequency, and it's basically input impedance versus frequency plot. What is the method used for fabricating the fine features of this antenna? So we have a laser etching machine. So it can print fine features up to say less than 50 microns. So it has like a laser that burns through the copper on a substrate, and then you just remove the copper. And my feature size was of the order of 100 microns, so it was not that difficult. Yeah, for soldering, we have like a machine. So basically, we have a solder paste that comes out of a needle, like just like a hypodermic needle. And you just put like 2 drops of solders on where you want to solder the inductor. And then you have to cure it at high temperature. So you have like a curing pad for that. You place the planar design on that and just raise the temperature of that pad. So it basically melts that solder and then cools it down. So basically the inductor gets attached. Okay, what are the main application fields of the electrically small antennas if the radiation efficiency is less? So like I said, these are for sensing applications. So basically, let's say if you have like a RFID or something, you are not tracking the RFID from like, let's say 1 kilometer distance. You are probably tracking it from a few meters. So which is why it doesn't really need a very high radiation efficiency. And also like the as you have seen, all these applications are narrowband applications. So these are the perfect field for electrically small antennas. How the impedance have been calculated, I have already answered that. Please share the okay. Is the far field of electrically small antenna at a distance 2d square by lambda. Okay, so far field actually is a controversial topic. So, there are three kinds of fields. One is the reactive near field, then there comes radiative near field, and then there comes radiated far field. So some people actually call the transition between radiated near field and radiated far field as the distance from where far field starts. And some people, on the other hand, actually prefers the other one between reactive near field and radiative near field. So they say like the far field starts from there. So that's lambda by 2 pi. And usually the other one is 2d square by lambda. Yes. But then again, for a dipole antenna, 2d square by lambda is not very appropriate because dipole is like a linear antenna, right? So it doesn't have a cross section, to be honest. So like while you are determining this d, which is the maximum dimension, you have no other option than considering the length of the dipole. So yeah, you can use 2d square by lambda, and beyond that point, like it will probably be far field anyway, so it's fine. Matching network is same as band pass filter. Yeah, you can say that because matching network will pretty much determine what goes into the antenna. If we use prototype 2 due to meandering and all, on the gain get reduced. Yes, you are right. So basically, for the lumped loaded case, we got like an efficiency of 35%. For the meandered case, we got an efficiency of 28 to 29%, which is slightly less, as you can imagine, because of the distributed nature, and that actually introduces a little amount of loss. Also, because of which the meandered case will have a slightly larger bandwidth than the lump loaded case. Then for an application of RFID, which one is better? Of course, the printed one is better, but we did the lump loaded case because to reduce the simulation time. Because otherwise, you can imagine like you have to meander all the like the driven arm there, and it will have the same problem. Okay, I have made a dipole antenna tuning from 120. How can I improve the radiation pattern and also electrical bandwidth? What do you mean by improving radiation pattern? Because if you are working around the half wavelength or below that, the radiation pattern will be omnidirectional. And how can you improve the bandwidth? I've showed you that example already. Like you just have to make it occupy all of that spherical volume within the Chu sphere. So try to make it like in the shape of a helix or spherical helix, like the ones I showed you, and that will do the trick. Are there any more questions?
Shivdar,
Yes, yes, sir.
yes, yes. Is there any other questions left for you? Any other questions?
No, sir. I have written in the chat box. It's in the chat box.
Okay.
Sir, before, shall we have a virtual photo shoot now?
What? Sorry.
Virtual photo shoot.
Sure.
Before that, I have some comment for the speaker.
Okay.
They want to have the virtual Photoshop. So for that, you have to turn on your Shambhu.
Really? I'm just wearing like a t-shirt and
We give you a minute to do that. To
okay.
change.
Okay. Hang on a minute then.
Yeah. After he changes his configuration, I will have the comment.
Am I visible?
Yes, sir, you're visible.
Yes, visible and looking great too.
Thank you.
Yeah. So I was there partially in the talk, but I am quite aware of Sangamitro's work, and he has really done very good work under the guidance of Ashil. And in fact, that entire lab, all of them are doing very good work. So he, in fact, has talked to a few of his colleagues, and they have agreed already to deliver the MTTS and that APS MTTS GC Barton Hill chapter. So that's a very good news for youngsters, because as you have seen, we are having different kinds of activities. Sometimes you are having very experienced speakers who have done significant amount of work on various fields, which you have named as L4. But that is one of the aspects. Definitely, we can hear from them. The other aspect is to hear from those who have written and they are still running in the track. So they will give a different perspective when they talk on. So I believe on that note, this talk was a very good talk, and many of you have got many ideas, and he's very helpful and supportive. You can write to him because you might have some other confusions or some queries be addressable initially at this moment. So feel free to talk to him on his behalf. I am telling this to all of you. And regarding Shambho, as I said, I don't want to talk very formally. One thing very specific regarding Sanghamitro Das is, he's a very good photographer. I know he almost spent 50% of his Canadian earnings in buying high quality cameras, lenses, and all. And some of his photos I know that have been collected from Canadian photo expo or exhibition, right? So, Shango, can you share your experience on that?
I have had my like moments, I would say. Yeah, I have had my moments.
But he will always click the nature and the scenic beauty. He will never click himself. That's why when I asked to send a good quality photograph for this flyer, he said, I don't have. But I said, you have spent almost more than 6-7 lakhs for buying camera and you don't have a photograph of your own.
Well,
Yeah. Some any other comments from our office bearers? Orijit, Anu, for Sanghamitro Das?
Yes, actually, this when I heard that he's from this Kannada Albert, I was just taking the time right there. And during the
4
starting of
a.m.
the
in the
lecture,
morning.
it was yeah, now it is 4 a.m. and you started at 2:30 a.m. I think.
Yeah,
So really,
Yeah.
we are really grateful that. Sorry for disturbing you so early, and
Oh,
we are really
I,
grateful.
I forgot. I forgot. Even though he stays in Canada, his working time still is Indian. Most of the time, he sometimes sleep only some early morning time, maybe 4 to 8 like that. I am very much aware of his daily routines also. So that is another feature of Shambho Mitro Das.
Yeah,
He
yeah.
can adjust to any time zone.
yeah,
Broadband.
broadband. Right.
So let's have the virtual photo shot and then we can call it a day.
I request all of you to turn your cameras on so that
Turn my camera where? Like, is this okay?
Yes, sir. It's okay.
Yeah, the light is not very good. I can't help. So,
Shango, you may please write your email ID in the chat box. Some of the participants are asking.
yeah, okay, I'll do that. Just holding the laptop with my two hands.
Thank you all. Now I invite Meher to deliver the vote of thanks.
Hello, am I audible?
Yes, Meher, you are audible. On.
So, good afternoon, everyone. I am Meher from Government Engineering College, Barton Hill. Today, I am entrusted with the duty of giving the vote of thanks, which I think is the greatest because nothing will be complete without the words of gratitude. Firstly, I would like to thank our speaker of the day, Dr. Sanghamitro Das, who is a research assistant from the Department of Electrical and Computer Engineering, University of Alberta, for giving us this wonderful lecture and finding time to interact with us amidst his busy schedule. I thank you on behalf of IEEE APS and MTTS GECB and everyone present here. Thank you, sir.
Thank you.
Next, I would like to thank Dr. Chinmoy Saha, Professor, Indian Institute of Space Science and Technology, Valliamala, and Chairperson of IEEE MTTS Kerala section for his immense support and valuable guidance. Thanks a lot, sir. I extend my sincere gratitude to Sri Ajit Mitra sir, scientist at VSSC and APS secretary, who's a mentor for many of us. Thank you, sir, for your immense support. Next, I would like to thank our pillar of support, our faculty advisor, Professor Anu Muhammad sir. Without his sincere effort, support, and guidance, we would have never accomplished what we have achieved so far. Thank you, sir, for your efforts. Last but not the least, I would like to thank all our participants whose presence made this event a grand success. Thank you all, and I wish you all a very good evening.
Thank you.